Look at this guy. I wonder what he's looking at. Do you think I should grow out my beard like that? Markovnikov's rule is probably the most important principle that underpins just about every reaction in the alkene and alkynes chapter. We have to understand what Markovnikov's rule says if we want to be true OChem ninjas. Markovnikov's rule was first described by Russian chemist Vladimir Markovnikov in the middle of the 1800s. Look at this guy. I wonder what he's looking at. Do you think I should grow out my beard like that? The electrophilic addition reactions in the alkene and alkynes chapter use an alkene or an alkyne as a starting material to react with some kind of electrophile, we'll talk about that in a few minutes, to form some kind of product. What we want to focus on here is the nature of the alkene. What is the major mode of reactivity of the alkene, and how can we use that to help predict how alkenes are going to react, and this principle that we're going to call Markovnikov's rule. When I look at an alkene, when I look at any new functional group, one of the things I want to do is be able to determine if that functional group is a nucleophile or an electrophile. I have a whole separate video linked down below on determining nucleophiles and electrophiles. I see this molecule has a pi bond between carbons 2 and 3. A pi bond is the sharing of 4 electrons between two elements. 4 sounds like more than 2, so there's an excess of electron density between carbons 2 and 3. That means that alkenes are nucleophiles. This is the major mode of reactivity for alkenes. Alkenes are nucleophiles. If the alkene's a nucleophile, that means it's going to be reacting with some kind of generic electrophile. The alkene's going to be reacting with an electrophile to form some kind of new bond. The next step then, and this sometimes confounds students, is where exactly are the electrons coming from? Which atom is the nucleophilic atom? How do I know which atom is going to form a bond with the electrophile? These are very good questions. Let's take a look at them and use those answers to derive Markovnikov. Let's look at the resonance contributors of this alkene. I could take this pi bond, these 2 electrons in the pi bond, and break that pi bond and deposit those electrons locally onto carbon 2. That will form a new resonance contributor for this molecule that has a lone pair and a negative charge on carbon number 2. In order to break this pi bond, we had to take the electrons away from carbon 3 to deposit them on carbon 2. So now carbon 3 lacks electron density and has a full positive charge. This isn't a video about how to draw resonance contributors. I have a separate video about resonance that I'll link to down below. But this is one resonance contributor for this structure. I can look at a different resonance contributor where I break the pi bond and I deposit those electrons locally onto carbon number 3. That will put a lone pair and a new negative charge on carbon number 3. We had to take electrons away from carbon number 2 to form this resonance contributor, so there'll be a positive charge on carbon number 2. These are the resonance contributors for this alkene. As I look at these resonance contributors, I want to be able to rank them in order of stability. The second best resonance contributor will typically define the molecule's reactivity. This is a really important ninja skill to learn, and I have a separate video on second best resonance structure rule down below. Certainly, the resonance contributor with all of the bonds and none of the charges is going to be the first best resonance contributor. The neutral molecule is the most stable. It's going to contribute most to the resonance hybrid. So I need to rank these 2 resonance contributors as number 2 and number 3. I want to look for the place where it's the most unstable, the least happiest place, and see how I can make that as stable as possible. The negative charge at least has a full octet. It's got 8 electrons around each of those carbon atoms. At least it satisfies the octet rule. The carbocation carbons only have 6 electrons around those carbons, so they're going to be the unhappiest. This isn't a video about carbocation stability. I've got a separate video linked down below about that. But the secondary carbocation is going to be more stable, so it will be the second best resonance contributor, and the primary carbocation will be the third best resonance contributor. This is how we can rank these resonance contributors in order of stability. The second best resonance contributor typically defines the reactivity of the molecule. If we know that alkenes are nucleophiles, if this is the second best resonance contributor, if carbon number 3 has the buildup of electron density, that tells us that alkenes are nucleophilic at the least substituted carbon. This is a very important point for alkenes. This is the major mode of reactivity for alkenes. Alkenes are nucleophiles. They're nucleophilic at the least substituted carbon. Every time we see an alkene, we want to think about it being a nucleophile at the least substituted carbon. I have an entire separate video down below about major modes of reactivity. Why is this a major mode of reactivity? Alkenes are nucleophilic at the less substituted carbon so that the resulting carbocation can be as stable as possible. Therefore, when this alkene reacts, it will react through the nucleophilic carbon, the least substituted carbon, to form a new bond with the alkene. When we draw our curved arrows for this reaction then, we'll use bouncing arrows. We'll start the arrow at the pair of electrons that's shared between the 2 carbon atoms, and we'll springboard the electrons off the least substituted nucleophilic carbon to form the new bond with the electrophile. This is an example of bouncing arrows. Bouncing arrows are a very cool new concept in organic chemistry. I've got an entire separate video on bouncing arrows down below. But this says we break the pi bond, we springboard the electrons through the least substituted nucleophilic carbon, and that carbon number 3 gets to form the bond with the electrophile. That will form a new intermediate with a new bond between carbon 3 and the electrophile. In order to form this bond with the electrophile, we had to break the 2,3 pi bond. We had to take the electrons away from carbon 2 so they could springboard through carbon 3. That's going to leave behind a new carbocation on carbon number 2. What happens next depends on exactly what the electrophile is, HCl, H3O+, BH3, MCPBA, but this is the key step. This is the step where we can finally describe what exactly Markovnikov's rule is. When alkenes react, they'll react through the less substituted carbon to form a new bond with the electrophile to give the most stable carbocation. This is Markovnikov's rule. Markovnikov's rule says that in an electrophilic addition reaction, the alkene will react with the electrophile to give the most stable carbocation possible. This is what we want to remember. The alkene reacts to give the most stable carbocation possible. It reacts through the nucleophilic less substituted side to give the carbocation at the most stable more substituted side. Now, there are other mnemonics, there are other ways that people talk about Markovnikov's rule, about where the H's are or where the cool group goes. I don't really care for those mnemonics because mnemonics don't tell you why something's happened. So when you get a new situation or a molecule that looks a little bit different than what you're used to, if you don't understand why Markovnikov's rule works, then you can't really be a true OChemNinja. Furthermore, with this last one, the cool group going on the more substituted side, that won't work with carbocation rearrangement. If all you memorize is that mnemonic, you will miss every carbocation rearrangement. And I've got a separate video on carbocation rearrangements linked down below. So when an alkene reacts, it reacts at the less substituted most nucleophilic site so that we can form the most stable carbocation intermediate possible. This is how OChemNinjas remember Markovnikov's rule.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.